So we got the two different things here that we're talking about, astromusicology, and we're going to be trying to answer these questions. Why does the Western musical diatonic scale label notes A through G? That's like pretty random. And then what is the spectral class, stellar spectral class, and how do astronomers specify it? How do these systems overlap, and what can we do with this information? So the first thing is it? Yeah, there we go. Okay, so that's it. So the first thing, the current musical, there's been many different systems for specifying, scales. And, but it's interesting because the current system that we use is relatively new. For a lot of history, they didn't have the same kind of, strict, names for every note or something like that, or even like having a staff or, a conception of each note as its own individual thing. Because in the past, it was a lot more, less written down and more kind of spiritual in nature, so people would have associations with a specific tone, and they would say it means this. And there was a whole thing, not in here, but in the past, where they banned specific, chords because they were like, oh, this chord is not good. Well, so that's interesting. But what I was talking about specifically here is that considering that the earliest musical instruments date back to 42,000 years ago, which was a flute, and we just have all of this musical notation developed just in the past 1,100 years, basically. So it's a kind of a relatively new development. And the 7-tone scale, diatonic 7 tones, heptatonic, comes from the 12 tones, and it's, specifically, you take the basic, if you have chromatic 12 tones, and then you have spaces between tones of 5 whole steps and 2 half steps in each octave. But it all actually comes from what sounds nice to certain people. And it's different for different people. And I say Western musical diatonic scales because for different places, especially around the world, there's completely different systems. And it's very specific to what we do. Though what's interesting is, and we'll get into it later, but for the spectral class, it seems to be more general. I don't know if other countries have different systems for that. So we have these. Let's see what we got. People, yeah. So there's like why 7 as a number, and so there's kind of some research I have here from Dr. Sean Hutchins, director of research for the Royal Conservatory of Music in Toronto. Said people can remember lists of numbers or words nearly perfectly when there are 5 or fewer, but accuracy drops drastically when the number goes past 9 items. People can remember a sequence of up to 7 tones, but not much more. And so it kind of has to do with the memorization thing, that you have that, not, a large, very big scales are not much smaller than that. But why A through G specifically is, it seems to be developed from, which is why I have this, Greece, where we have first systems were, that labeled scales with letters seems to have come from Greece. And we have 2 Greek notations were of this type, and there were many comparable notations to the modern ones arose around the Middle Ages, when you first had this great body of liturgical music that they started to want, like, well, we should write this down. And they're like, so trying to develop a system that they can actually, record that, which wasn't really a necessity until then. And so that's why we have, one of the reasons why we have this kind of recent, big build-up in musical notation. And so we end up with A through G, just as the labels for those 7, but there were other letter systems used. And so this is just the current one that won out. And then, cover that. Yes. Okay, so this is the thing. So it says, this whole story of the development of musical notation, it mirrors how astronomers have attempted to classify the stars, and both that you needed to develop a precise system of notation that also can efficiently encode data. And so, kind of a similar thing happened with the stars. This is lovely James Webb Space Telescope, Eclipse of Creation, Cosmic Eclipse, that's what it is. And it's one I like a lot, but there are a bunch of other ones. It gets overused, to be honest. But if you want to go for why we currently use the system we use for classifying the stars, I guess it's a little premature. We wanted to, the two main factors that are important for classifying stars are luminosity and spectral class. That's what we currently use. But that came from older characteristics that could be easily observed, which is just color and brightness. Where it's like, oh, it's a dim red one or a bright blue one or something like that. You don't have much information with the star, but you have a little. And they do vary if you spend enough time looking at them. You can say, oh, that one looks different than this one. And so, so it comes from the observable properties. Now, some of the first systems that we have that classify these kind of things, again, comes from Greece, which I have been noticed, like, they did get up to a lot. They did a lot of stuff. There's a lot of stuff that originates in, ancient Greece. And the original developed a system for sorting stars. Many Greek astronomers did, but notably Hipparchus, I think I'm pronouncing that right? Hipparchus developed a system for sorting them optically via their brightness just to the eye. But that system, so it says Hipparchus, according to, this is actually from the textbook that I took for one of my classes, designated the brightest star in the sky as first magnitude, and then the next brightest as second magnitude, and so on. With the faintest visible stars were magnitude 6. And today we call that designation apparent magnitude because it was just based on from Earth. It's very Earth-centric. That's how bright those stars are from here. But if we wanted to have a more objective system, we would need something like absolute magnitude, which parallels to luminosity, because absolute magnitude is how bright the star is at a given distance, and that brightness, luminosity, is the radiative output, how much energy it's putting out. And so that if you have a specific distance, it'll have a specific brightness for the given stars. So that's how we get that half. And then the other half, which is more important for this particular nonsense, is that the classification system, over time we learned more and understood that the stars weren't, just points in the sky, that they're actual bodies. And so we want to know more about them. And one of the big things people were trying to figure out was how you can relate temperature and color and composition. And so for that, the spectral class becomes crucial. It's kind of a complex topic, and I don't know about everything there is. It's quantum physics, heliophysics, spectroscopy, and astrophysics. But to simplify, with the advent of modern telescopes, we've been able to observe the connection between the temperature of a star and its color in visible light. And because this is because stars are objects that emit light based on thermal radiation. And so we can use the laws of thermal radiation to determine their temperature based on their color. And so if we take a spectrum of that light, which is splitting it into the bands of the rainbow, there are visible, this is Hipparchus. I forgot that. Yeah, this is like, I don't know what this is giving, like what this
his
is
orb.
representing. It's like
the orb he ponders.
It's a side eye, I don't know. Anyway, this is what I was talking about. Was you get these bands in the spectrum that represent absorption lines, where various atoms and molecules absorb the light at that specific wavelength. And the reason that happens is complicated quantum mechanics and orbital shells and stuff that I won't get into here.
We'll learn this in chemistry.
Yes, and we are. And this is what's fun, is in my current chemistry class, I have some inkling of what we're talking about because I know about it from this. And so, based on that, we can determine temperature, and the reason we can do that is certain things for them to absorb. For example, stars displaying spectral lines of highly ionized elements must be fairly hot because they have to be hot enough to actually ionize those atoms, because we can tell what they are based on the light. And so, whereas if we see the spectral lines characteristic of molecules, it must be relatively cool to allow those molecules to actually form. And then we've organized, so this is where we get into this whole astromusicology business, is that we've organized the spectral classes by the 7 letters OBAFGKM, which is like, it's interesting, with O-type stars being the bluest and hottest, and then M-type stars being the reddest and coolest. which kind of gives you that temperature-color relationship, which we get again from the spectrum. So, with that, there's subcategories where we broke it down further into from 0 to 9. So the hottest stars would be O0, and the coldest stars would be an M9 star. And so the important thing that I think is important to talk about is that you have OBAFGKM. It's like, that's not how the alphabet works. Why have we done this? Why have we not said that the brightest one is A0? And there's like, and then it goes from the, and it was like, is this because astronomers want to make things unnecessarily difficult? No, it is because of 2 words, which would be legacy data. And so the original documentation system of the spectrum was the result of the diligent work of the Harvard Observatory computers, which were a group of female astronomers, Wilhelmina Fleming, which is we have here, which is 1857 to 1911, was the first to classify the numerous stellar spectra gathered by the observatory. And so this is one of the first times that you had this buildup of data, just like how we had this buildup of all of this musical, liturgical music, and so they needed a way to classify it. And so she organized these stars with their hydrogen line emissions from the A to O, with A being the strongest, most visible line. So that's kind of this logical alphabetical order. But as more spectrum were collected, Annie Jump Cannon, 1863 to 1941, building on the work of Fleming and another astronomer known as, and I think it's Antonia Murray, or I might be mispronouncing that, realized that the spectral classes fell into a natural order that wasn't the order they had classified based on the hydrogen line emissions. And so that natural order, rearranged them, is OBAFGKM. And so it's convenient, but no one knew why they fell into that order until Cecilia Payne-Gaposchkin, which is 1900 to 1976, realized that the star's surface temperature determines the strength of the emission lines. And then rather than re-lettering the old system and reclassifying all of that legacy data they had built up over all that time, they simply, just have the strange old, letter ordering, or like, this is the way it is, and we're not going to fix it. And so, as a notable later invention was the idea conceived by a Danish astronomer, Einar Hertzsprung, and independently by U.S. astronomer Harry Norris Russell, which was to plot luminosity against stellar class on what is now called an HR, or Hertzsprung-Russell diagram. Which these are those 2 people. We got this guy is the Danish one, and this one is the American. Okay, so this is what that graph looks like. There we go. This is what it looks like, where we have the color and the temperature, and then the brightness. And this is a very useful thing. It's kind of like the periodic table. I always think of it that way. And then it gives you way more information than you think. There's all this really useful stuff that's in this. But I don't necessarily have time to talk about it all at the moment. But it's worth looking into.
What's it called again?
Hertzsprung HR diagram, or Hertzsprung-Russell diagram. Meaning it's like I say, like the periodic table. There's just so much encoded that you can get from this. And you see those mass levels because there's a correlation there between mass and all of this. And then if you plot a star's life on this, you can get even more information and predict things. It's very useful. And so then, now, so this is the not conclusion, but the point where it all comes together. So as a result of all this, one moment. As a result of all this, because we have these lettering system for the stellar spectra of a star, and because we have, we've converged from these 2 different systems for classifying disparate phenomenon to these lettering systems with the zeros 1 through 9. As a result of this, we can convert stellar spectral class into musical notation. And for any stars of type B0 through G9. And so if we do this for something like the North Star, Polaris, we get that the North Star is an F7 class star. And so if you, for example, convert that into an F7 chord, that will look like this. And it will sound, and I might be doing this wrong, but something like, I think, And then if you were to take another example, is the star Deneb. I don't know if any of you have heard of it, but it's another bright one. Is right here, is an A2 class star, and if you convert that to a chord. So what's interesting about this is you could convert it into, some of them, you can convert not only into chords, but also notes conveniently, whereas A2 is a specific frequency as well. So you could also play the stars as individual notes. But as a chord, that would look like that. And I'm not sure if I can play this one correctly. Let me just see the, A2 should be something like that. And so, with this, you can take stars and you can write a song with them. And so I did a brief mock-up of this, which is a bit grating, honestly, because I did it using a chiptune 8-bit music simulator, but it is accurate. It's scientifically accurate. And so the transcription of what I will play, and I apologize if it's grating, I can always pause it. But, so this is Sigma Draconis, which is a G9 star, Zeta, I don't know how to pronounce it, Zeta something, which is an F9, and Pi 1 Boots, I think, I already forget. It's a B9 Canopus, A9, and with just those rearranged and then converted into sound would sound like this. Let me make sure the volume.
Let's go! Woo. It sounds like Pokemon music.
Yeah, that's what I was just thinking.
Yeah. Sounds like you're entering the Eterna Forest or something. Oh.
That was not supposed to happen at the end. But yes, that was all stars.
Yay! Nice.
Nice music.
Thanks.
Yeah.
Are there any questions?
Could you convert songs into stars? If you just have the chords of the song, you just assign
Yes,
a
you can
star.
do that too. Yeah, I haven't thought about doing it the other way. It's interesting because with all of this, you can do so much with this. My brother's a professional musician, and I've been really trying. I need to reach out to them and ask them to do something that's kind of fully orchestrated or something like that. But another resource that I was thinking, it's incredibly specific. It's a highly specific application of this. But if you had an astrophysicist who was also blind and had perfect pitch, then you could encode data, stars, as notes and just play them for them, and then they would automatically know what the pitch is, so they'd know what type of star you were talking about. So it would be a very efficient way of encoding data. But it's highly specific. Yes. So there's that as well. Yeah. Were there any other questions? Or?
That's awesome.
Thank you.
Yeah.
And it'd be so cool to like write out constellations using that.
Yes, and so not all of the stars fit in, as you can see here, the ones that actually line up with musical notes. There's no O, we don't have that as a note, although it's something weird. It's like in German musical notation or something, they might have an O or something like that, I'm not sure. But these ones in the middle, we got E, A, F, G. Those ones all convert to chords, and then also as we have this, 0 through 9, those can be, tensions. And so I don't know if I clarified that for people who aren't as familiar with musical notation. When you have like a G2, it's G suspended 2, and so it's tensions on top of the, initial chord. We're like adding an extra note on top of it, or below, I guess, technically. Yes, and then there's a lot of abbreviation that goes into all of these things. But it's a fascinating thing, and I discovered this while I was taking a astronomy introductory course, and I was like, there's no one I can tell about this. It's like you can't corner someone for long enough unless you get the presentation. So thank you.
Of course.
For the opportunity.
Yay!